Hello everyone, my name is Tiffany Roberts and this is my Lab 3 presentation. In this lab, we are analyzing the parallel and perpendicular forces acting on a star throughout its orbit around a black hole. Using this information, we will then approximate the mass of the black hole. In order to do so, we utilize Newton's second law and the principles of two-body motion that we have learned so far to analyze perpendicular and parallel net force. Additional concepts we use will be parallel and perpendicular momentum change, as well as using the gravitational force equation to predict the mass of the black hole. Once again, the main principles and concepts used are Newton's second law, force equals mass times acceleration. We use the position and velocity update equations, which are given in the starter code. And we must consider that the only force in this problem is gravity. The gravitational force equation is used to find the mass of the black hole. The perpendicular and parallel momentum change equations are also used, and it's important to note that the parallel equation deals with the change in velocity in the direction of the motion, and the perpendicular equation deals with the change in the direction of the velocity. Here I will begin talking about my glow script code. Here I am setting the initial conditions for my code. As stated in lab instructions, I set my seed equal to my Georgia Tech email. I defined capital G as the gravitational constant. I plugged in the star's mass given to us in the problem statement to be 2.0 e plus 30 and defined delta T as 86,400, which is the number of seconds in one Earth day. Moving into the while loop. Here we are calculating the initial velocity and momentum and final velocity and momentum by taking the difference of consecutive data points that were generated in the code. The delta P that is found is then divided by time to calculate the instantaneous dp dt, which is directly equal to the net force. Still within the while loop, I wanted to break down the parallel and perpendicular forces. So first I calculated the unit vector of the initial momentum in order to find the direction in which the parallel component of the change of momentum would act. I then solved for the change in magnitude of the momentum using a difference of standard magnitude equations between the final momentum and the initial momentum. Using this value multiplied by p hat, I obtained the change of momentum in the parallel direction. This value is directly equal to the parallel net force. Next, using the known overall change of momentum and parallel change of momentum, a simple subtraction obtains a perpendicular change of momentum, which is then directly equal to the perpendicular net force. Once again, still within the while loop, this segment of the code is dealing with calculating the mass of the black hole. So, rearranging the gravitational force equation to solve for the mass of the black hole, we get the mass of the black hole is equal to the magnitude of the net force times the magnitude of the distance between the star and the black hole squared, all divided by the gravitational constant times the mass of the star. Below is the code which represents the equations in the first circle. The second circle represents the part of the code where the star position is updated for the next loop and a trail is left behind for visual purposes. This part of the code is used to represent the net force and its perpendicular and parallel component, each arrow originating at the star as noted by star dot position. For the arrow length, the respective vectors calculated previously in the code are directly used with only an arbitrary arrow scale modifier being used for proper visualization purposes. We note as it starts to go around that the parallel force begins to grow as it nears the closest point to the black hole, then changes direction once it passes the leftmost point. This is consistent with the star's motion being the fastest at the leftmost point and slowest at the rightmost. Also, we note that the total net force always points directly to the black hole, while the perpendicular force seems to point to the center of the imaginary kissing circle at all times. I calculated the mass of the black hole to be 4.42563 e plus 30 kilograms. So what does it mean? In your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So in the code, it's denoted that the parallel momentum change component is equal to the parallel net force component, and equivalently, the perpendicular momentum change component is equal to the net force perpendicular component. This is because the values are the same. However, the quantities are conceptually different. The changes in momentum are representative of the physical changes being experienced by an object in the way of speed and direction, while the respective forces are physics measures of actions of the object from other objects. What if? Imagine the black hole whose mass you found was removed, and a different black hole was replaced in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? In other words, is it possible for you to find a value for the mass of the new black hole that is different from the mass you found for the original one? Well, since the motion of the star is said to be exactly the same, and we know the motion of the star is governed by the force of gravity, therefore the new mass of the black hole must be unchanged from the original black hole. This concludes my Lab 3 presentation. Thank you so much for watching.